Hi, Calc 2 students. So we are going to pick up our exploration of finding different quantities using integration with one cool application, which is we can use integration to find exact volumes. So in previous videos, we've seen how we can find areas underneath and between curves. And now I'm going to invite you into the three-dimensional realm. So let's imagine for a second a three-dimensional region. And you might remember that if we're in 3 dimensions, a classic XY axis is not going to be sufficient. We need our third axis called the Z-axis. So if we look at this loaf of bread, it is a 3-dimensional object, and we have the goal that we are going to try to, let's say we're going to try and find the volume of this bread. So continuing on our understanding of how we approximated area, you will probably remember that we use areas of rectangles to get an approximate. That is going to be the same concept, but now instead of having rectangles, we have slices. So with this loaf of bread, you see we've already got it cut into slices here, and our slices are the same width, right? So our strategy is going to be, we're first going to approximate the volume of one slice, and then we're going to add up the volumes of all the slices. So let's give things some official formulas and names. So let's call the thickness of this bread, each slice, we'll call it a delta X. Okay, and why delta X? Because if you look at the thickness here, it is a width along the x-axis. So when we say delta X, that means change in X, and it can be found by finding a difference in the X coordinates where each of the cuts are made. They are uniform, so we're just going to call it globally delta X, just like we did with our rectangles. Okay, so if you think about finding the volume of a single slice of bread, when we think about volume of a prism, which is a 3-dimensional solid that has uniform bases, and then it's just connected with parallel lines, you'll see we have that. So our bread is a prism. It's got a weird shape, but the other side is the same weird shape, and it has a thickness. So how we're going to find the volume of a single slice is we need to find the area of the little bread face here. So we need to find that area. And how we could do that is by using a function, an area function. So we'll go ahead and call the area function a of x. Okay, don't worry, we're not going to do this exact example on this bread. We don't have actual formulas for the loaf of bread, but for our solids that we're going to explore with exercises, we will. So for now, we're just speaking generally, and we will call the area of the slice of bread a of x. So now we can find the volume of our ith slice of bread. So how are we going to do that? We have the area times base area times height is the formula you might remember. So the base area of the ith slice would be the a of x sub I times the thickness, or as we learned back in geometry, base area times height, and the height here would be delta x. Okay. If you need a little refresher of the geometry there, just think about how we did it with like a rectangular prism. Like if this was a more basic shape, we would find the area of the rectangle here. So that's kind of like our a of x sub I, and then multiplied by the thickness, right? So same concept there. Okay, so then if we wanted to approximate the volume of the whole loaf, well, we're going to repeat this process, but we're going to add up the volumes of the slices. So using our sigma notation and noting that if we have n slices, big N slices, okay, we are going to be computing a of x sub I times delta x, which is, like we learned last time, x sub I minus x sub I minus 1. If we want to be more specific, and the I is going to range from the very first cut up until n minus 1, which is when you stop cutting to get n slices. Okay, so that is the approximate volume of the whole loaf, and the exact volume we could find with integration, which would be found by letting the number of slices go to infinity. So this is a very similar formula to what we did with our two-dimensional regions. And we learned that this limiting our Riemann sum gives us an integral. So where you start slicing the bread to where you stop, the area function. Okay, that is where the concept comes into play. Okay, so this is just a general example, and the slices of bread is just kind of a fun play on it. We're not going to worry about finding exact formulas here, but this is just a three-dimensional extension of the exact process that we did with our rectangles. So I want you guys to have that in your mind as we work through these. So let's go ahead and move on to a nice example here. We're going to consider the region bounded by y equals x squared, x equals 1, and x equals 4. We will find the volume of the 3D region whose cross sections are squares with one side in the xy plane. Okay, so let's try and visualize what this is, what we're talking about here. So there is a three-dimensional region that's being described, and here I've already sketched for us the two-dimensional region. So this is just the xy plane. And the solid that we're describing is, imagine that the cross sections of this solid are squares. So if I look at what this solid looks like, it's not quite just as simple as finding this base area because it's not a prism. So what you're imagining is you have your rectangle. If you cut a rectangle here, right, and it pops up out of the page, this length here, the height of the green rectangle, is also going to be how far it sticks out of the page. So because these rectangles change continuously, like when I pick a point that's on the curve, the rectangle isn't completely on the curve because the parabola is changing too much. The curve is going to be smooth, so it's not going to be made up of these choppy little rectangles, but remember, that's why we said, okay, a Riemann sum approximating the volume is going to be when you look at the slices, a discrete number of them, versus the exact volume is when you look at the integral. So the construction of this, it's described, we're looking at these like certain number of squares. Okay, so let me try and use my art skills to draw this for you. So if we look at our region here, okay, here's the base, because it says that one side of the base is on the xy plane, and then the height here, a green rectangle. It's going to be a square, the same height as the rectangle. And then the next one, okay. So imagine the solid like popping up out of the page, and the height that it pops out is the distance from the blue curve to the x-axis. Okay, so when it was all said and done, the height would be kind of varying on the top. So it would kind of like curve out like that. Kind of hard to make it look curvy enough here in 2 dimensions. But it would kind of look like a slide. Kind of look like a slide on the side. Okay, but that not so great illustration that I did is fortunately not needed to find the volume here, because remember, we're going to think about our concept. So let's go with our strategy of finding the volume of the ith cross section slice. Okay, so the cross section slices, they're just squares. Okay, so I'm just going to draw the square. I could draw a better square than that. There we go. There's my square. Okay, so there's one of my cross-section squares, and we're going to write down the volume here. So the thickness of this is going to be a delta x. Okay, thickness is going to be a delta x. And the area is going to be however tall the rectangle is. So if the rectangle is, let's say, given by this blue parabola is y equals x squared. Well, the height of the rectangle is a point that is on the parabola. So it should be f of x sub I. And then if you think about top minus bottom, the bottom is the x-axis. So the height of this would be f of xi, technically minus 0. But we don't tend to write that. You know, we would just say f of xi. But top minus bottom is a good habit to get into in case your region wasn't bounded by the x-axis on the bottom. So just f of xi is this distance here. And it's positive. The curve is in the first quadrant. So f of xi will be positive. And then since it's a square, okay, cross sections are squares. We know about squares. They are uniform length and width. So this side would also be f of xi. Okay, so what would the area here be? The volume of the ice square would be x sub I squared times delta x, so the volume would be x. So xi to the fourth delta x. Cool. Okay, so there's the volume of the ice cross section, and this will generalize to any rectangle where we want to do it. And then the last thing when we think about our Riemann sum, and we're going to add those up. xi to the fourth delta x, I goes from 0 to n minus 1. This is the approximate volume. Okay, and so this means we've added up all the different volumes of a certain number of slices. Okay, as n goes to infinity, delta x goes to 0. And to get the exact volume, we get an integral. So the delta x goes to 0. We are then integrating the curve x to the fourth with respect to x. And then where are limits of integration? It's from where you started slicing to where you stopped slicing. So we started slicing, if you look at our figure, we started we call it a partition. We partitioned starting at 1 and we ended at 4. So this is going to be integrating from 1 to 4. Okay, I'm going to highlight the key components here. I want to keep reminding you how these are all related to each other. Okay, my personal preference for as you're working through these examples is to have each of these steps down, because the concept of setting up the integral is so much more important to me than just the arithmetic and computation that goes into computing an integral. And we have a lot of technology to help us with the computation of integrals. So my preference is focus on this setup, and the integration is, you know, just the very final, not worth very much part of these sorts of problems. So yes, to answer the question, I do want to see all these steps. These are all steps that I'm going to want to see if I was, you know, giving you a test on any of this. Looking at the problem as a whole, that's how it came together. So if we want to find the exact volume, the integral that gives it is there. We can actually go ahead and compute it. Remember that Wolfram alpha is there for you on things like this, but this one's a pretty easy integral, so it would just end up being 1/5 x to the fifth evaluated from 4 to 1. So using Wolfram alpha there to help out with the arithmetic, that ends up being 1023/5 for our exact volume. Pretty cool. So notice I did not have to draw the actual three-dimensional figure. It's very hard to draw these as part of the solution process. Let's go ahead and take a look at another example here. So let's consider the region bounded by y equals x squared and y equals 8 minus x squared. We are going to find the volume of the 3D region whose cross sections are semicircles in the xy plane. Okay, so if cross regions are semicircles, what that is going to look like is if we had our little rectangle here, the ith rectangle, we drew it in, that is going to be the bottom part of a semicircle. Okay, so imagine it's a semicircle. And just to kind of refresh your vocab on the different parts of the circle, what part is it when you have like a half circle and it's this whole length? This is the diameter. This is the diameter, which you might remember is 2 times the radius. Okay, so diameter is twice the radius. So basically we have like a dome. There's like a dome top and the base is also this kind of like eye shape. So it's like a dome coming off of the eye shape. And again, drawing these is really hard. Some of us struggle with it more than others. So please don't be consumed in trying to draw this. This is why computers are absolutely amazing for all that they've allowed us to do. Okay, so now I have a concept of what the ith slice is going to look like. Let's go ahead and find the volume of that ith slice. Okay, so when I look at what became the base looks like it is going from the red curve to the bottom curve, and the thickness of it is a delta x. So this little thickness is a delta x, and then the height of it, which is this bottom part, would be the diameter, is going to be red minus blue. So think about that. We got point on the red curve, point on the blue curve. Okay, and you'll notice my rectangles don't entirely stay on the curve because just like how we had to do this with either the left, right, or midpoint rules for rectangles, we have that same concept going on in a 3D sense here. So this is sketched like using the left rule. So looking at this, we have a red minus a blue. So to get the height, it's going to be, looks like red minus blue is 8 minus x squared minus x squared, so 8 minus 2x squared. Okay, and then the radius of that would just be 8 minus x squared over 8 minus 2x squared over 2. So the radius of that would be because radius is half the diameter. 4 minus x squared is the radius. Okay, so the reason that I'm thinking of the radius here is because when we try and find our area here, when we try and find the area function for that semicircle, we have to use the radius. So you might remember we have this general concept here. The area times the thickness, and the area is pi r squared for a semicircle, and then split it in half. So pi r squared gives you the whole circle. Pi times 4 minus x squared, quantity squared, over 2 gives me half of the circle area. Okay, so there's the volume of the ith semicircle. Pi times 4 minus x sub I squared, quantity squared, over 2 times delta x. And no, we don't need to simplify the algebra yet. So then the Riemann sum. Okay, remember you have n slices. Your index ranges from 0 to the last slice you'll make. And then you have the area function, pi times 4 minus x sub I squared, quantity squared, over 2. And then delta x. And then that gives you your approximate volume. And then your exact volume. Is found as n goes to infinity the thickness of your slices goes to 0, your accuracy increases, and you have your integral. So the delta x part goes away. We drop all the x sub I notation. We just have pi 4 minus x squared, quantity squared, over 2 dx. And we are going to integrate that from where do we start slicing to where do we stop. So we're working left to right. We start at the intersections. Okay, so this one seems like it's going to be symmetric on both sides. I'm going to move it down. We have to find out the limits here. So finding limits of integration is coming down to finding the intersection points there. So how we do that, remember from previous videos, we go ahead and set our two curves equal to each other, and we get 2x squared minus 8, which ends up being x squared minus 4, which is 2, x minus 2, x plus 2. So it looks like it's going to intersect at 2 and negative 2. Okay, so we're going to be doing our slices from negative 2 to 2. Okay, so there is our exact volume. And will we learn methods to integrate this? Yes, we will. Our integration techniques are coming up. So for now, as we just kind of focus on this physical application, remember we've got Wolfram Alpha in our pocket to help with the computation there. So when we want to have Wolfram Alpha compute something, we can tell it to take the integral of pi times 4 minus x squared, quantity squared, and it's all over 2, so we'll do pi over 2, from negative 2 to 2. There we go. So just checking that our integral is what we intended it to be. Yep, that looks good. And it is 256 pi over 15 for the exact volume. So I'm going to go ahead and highlight things that I would be looking for in your work. I would want to see all of this. So this finishes the concept of how we can find certain three-dimensional regions using this slice technique and adding up the volume of the slices. In our next videos, we're going to go ahead and look at how we would find volumes of revolution with a kind of different method of slicing. See you then.